want to thank you for joining the webinar. We'll allow some extra 5 minutes. We'll allow some extra 5 minutes for more people to join. After 5 minutes, we'll begin the webinar. Thank you once again for joining, and we'll begin shortly. Thank you.
My name is Josphat Kimani, and I work for Merck. And I am the field marketing coordinator, coordinating all the marketing activities for the Lab Water Solutions in Eastern Europe, Middle East, and Africa. I'm based in Nairobi, Kenya. And I've been with Merck for over 7 years now. And I'm very happy to take part in today's webinar on lab water. And I would like to thank our partners, Cleanearth, for organizing this. And also, I take this opportunity to warmly welcome you to this session, where we are going to deep dive into matters of laboratory water purification. So, as you may know, and just like I mentioned, I work for Merck, and the lab water solution business is part of the Merck portfolio. And Merck has been around for over 350. Now, actually, it's 355 years. But the water purification business started slightly about 50 years ago, around 1967, when we entered the market and actually created the market for lab water purification systems. So I can comfortably say that we are the global leaders in water purification systems, and with over 50 years of experience. Before we entered into the market, what used to be there is just the normal distillations and the normal deionization. The rest has really evolved since 1967. So we offer a total solution when it comes to laboratory water purification. And we also offer in terms of the knowledge about water purification. We also offer knowledge about the technologies that are used in water purification. And we also offer the service. And this actually, in most of the region, we are partnering with various institutions like Cleanearth to offer that after-sales support, which is really important. So, as you already know, also water is the most widely used reagent in the laboratory, and therefore we cannot compromise on its quality, its reliability, and also robustness of the machines that are used. As Merck, we enable the scientists to produce the right quality of water in their laboratories. Hence, they are able to focus on their core work. So actually, when it comes to water purifications in laboratory, when it comes to all work in the laboratory, actually, it's only water that the scientist is able to produce in their lab. Most of the other reagents, they are bought, and they're bought from various institution, but for the water, the scientist has the capacity to produce the quality that they require in their laboratories. So really, it's all about making our scientists able to produce this very important reagent in the laboratory. I've just quoted a few critical laboratory segment, like the clinical market, like in the pharma sector, and also in the research world, and much more. water is the main reagent in the laboratory, and it plays a pivotal role when it comes to various activities in the laboratory. I'm just going to name just but a few, but water finds its use in preparation of blanks, especially maybe when running the HPLCs, or even when running the chemistry analysis, or even in the biomedical market. It's also used in gel preparations and also in staining. When it comes also to chromatography, like liquid chromatography, water is also used in preparation of mobile phases and also preparation of buffers. Also in sample preparations, like for example, in pharma sector, water is being used for in dissolutions, in preparation of standards, in washing and rinsing of sample and reagent containers. And also water is used in the water baths, in rotary evaporators, in tissue processors, in autoclave. So basically water has a lot of, it plays so many roles in the laboratory, just to name a few. Water also, there is basically some effects of contaminants in water. As you already know, water has contaminants, and we will talk about those contaminants. And when it has some contaminants, there are quite a number of effects that could come with the contamination of water used in the laboratory. And one is difficulties in data interpretation, because once you use contaminated water to do analysis, the data you get is not the desired results, and therefore the interpretation will be very difficult. There's also potential of the instrument that you're using to get damaged. So here, for example, if the water has particles and colloids, there is likelihood that the instrument that you're using could get damaged. When it comes to, for example, liquid chromatography, where columns are used, there is reduced column lifetime due to the organics maybe present in the water and so many other contaminants that could be present in that water. There is also the potential of loss of samples and reagents. Loss of samples, especially when you have very little sample. So if you're required to repeat the analysis because of contaminated water and you had small samples, then it means that your sample will be gone. So there will be no more experiments to be done. And also, if you need to repeat if you get wrong results, there will be need to repeat the analysis. So the other reagents used before will be lost as well. So there is increase in running costs. Erroneous results, need to repeat the analysis, and also to some extent you'll have need to do troubleshooting, because it may not come to your mind that the problem is coming from the water. You might suspect other sources of issues. That was just a brief summary about the water, the role, and so on. And in the agenda for today, I want us to go through the water contaminants and water quality monitoring. Second part is for us to look at the impact of water quality on the results of various analyses in the laboratory. And the third part is how water is purified. And here we will look at some of the modern day technologies that are used to remove various contaminants from water, and how to select the right solution. The right solution in this case is the right water purification system. So the first part here is we start with water contaminants and the water quality monitoring. So the natural water contains 5 main classes of contaminants. So as you already know, water is the 2 hydrogen atoms and the oxygen. But then inside that would be the ultra pure water. But then the natural water, which is the source of or the main source of raw material to produce laboratory grade water, contain 5 classes of contaminants. And these are the organics. You have the bacteria, you have the ions. Here we are referring to the positive and negative ions. We have, that is cations and anions. We have particles and colloids. These are the non-dissolved. And also the 5th one is the dissolved gases. So these contaminants, if they may have negative effects on human health, are removed down to safety levels by the water companies. And this is now at point where we refer to this as potable water, which is now can be consumed by human beings. The potable water, tap water now, still contains some of these contaminants at levels that are not harmful to humans. However, even at that level, these contaminants can be detrimental to laboratory instruments and experiments, and therefore these contaminants should therefore be monitored and removed to acceptable levels by appropriate techniques. And obviously these techniques, we'll find them in the water purification system. We'll go through some of these. And when the effect of these contaminants are very well known, then they should be removed as much as possible to make sure that they do not affect the experiments. So these are the 5 main contaminants that are present in water, and they should be removed to levels where it will not affect the experiments in the laboratory. And this is where now the water purification system comes in. There are 2 main parameters that require to be monitored during the water purification process. So the process in which we are removing the contaminants. So we need to monitor 2 main parameters, and these are resistivity through conductivity, and then there is TOC. So you have resistivity, which is basically talk about conductivity as well, and also we have the organic purity, which is total oxidizable carbon. And therefore the system, the water purification system, should be in a place, should be capable of showing you the quality of water with reference with these 2 parameters. So, and in order to deliver significant results, obviously the water purification system requires a proper design. And this is to be able to adequately measure, and also to have some alarms if there is a defective measure. There is also, the system should be possible to be properly calibrated, and should also be able to respect the norms from various institutions like ISO, from ASTM, from CLSI, or from CAP, various, or even from pharmacopoeias. So should be able to respect all those norms, and this will give assurance that this water purification system is able to provide the right quality of water. And I can say that the Merck water purification systems, the meters that are used to measure all these parameters, are able to deliver the right information for the customer. So they meet all these criteria in terms of proper design, proper calibration, and also respecting the norms. So maybe we start with the conductivity or resistivity. So, and basically conductivity will allow with a single figure to evaluate the ionic contamination in water. So basically, this is the measure of material's ability to conduct electric current. And conductivity and resistivity are used to define the overall ionic purity or the level of ionic contamination in water. So there is this relationship between conductivity and resistivity, where resistivity is equals to 1 over conductivity. So there is this inverse relationship between conductivity and resistivity, or you can say conductivity is equal to 1 over resistivity. So what is also very important is to notify the temperature at which conductivity or resistivity is measured, because these two are strongly dependent to temperature. So it's very important. So most of the time we will always report it at 25 degrees centigrade. And just to mention here is that the minimum theoretical conductivity is 0.055 microsiemens per centimeter at 25. And the maximum theoretical resistivity is 18.2 mega ohm centimeter at 25. If you do the math here, just to prove this relationship here, if you say 1 over 18.2, you'll find that it will give you 0.055. That is the relationship. So if you say 1 over 18.2, it will give you 0.055, and 1 over 0.055, it will give you 18.2. This is the relationship between conductivity and resistivity. The other parameter that we mentioned that is very important is the TOC. And the TOC is the measure of all organic substances that can be oxidized that are present in water. It is basically expressed in parts per billion, which is equals to microgram per liter. And obviously, you know that the tap water, which is the raw material used to produce pure or ultra pure water for laboratory applications, may contain many different oxidizable carbon substances, mainly dissolved in that water. So the TOC value will allow us to evaluate the organic concentration in the water. Just the same way conductivity allows us with single figure to evaluate the ionic contamination in water. So mainly what's normally is happening is you have a UV, a photo oxidation UV that is used in the water purification system, and then there is detection of the TOC level. So when we talk about the laboratory grade water, many of the organization, the international organization or the regulators normally classify water as type 1, type 2, or type 3. So normally type 1 is the most pure, which is used for critical applications like chromatography, that is liquid chromatography or liquid chromatography mass spec. Also used for elemental analysis, that is the graphite furnace atomic absorption, or in the inductively coupled mass spec, and also used in molecular and cell biology. So basically this is ultra pure water, which is used for critical application. And then we have type 2 water that is used for standard application, like buffer preparations, like in microbiology media preparation, in washing machines. So mainly the standard application. Then we have the lowest grade, which is type 3, and this is for non-critical applications like non-critical rinsing, used in heat water baths, in lottery evaporators, in autoclaves. So these are the 3 main types of water that you can get from the tap water. So to produce basically laboratory grade water, you start obviously with tap water as the main raw material. Then you go into the first stage is type 3, second is type 2, and then you have the ultra pure water. So when these are the two main stages to produce laboratory grade water. So what we have here is the feed water, which is tap water. So we have this pre-treatment stage, which is very critical. And at this point, based on the purification technologies present in the water purification system, you can either have type 2 or type 3 at this point in the reservoir. And then from that, you can polish that water to ultra pure water, which is type 1 water. You can see the two main parameters that we talked about, the ionic content and the organic content. So at the start, we have the concentration at ppm level. And when we are at pure type 2 or pure type 2, we are at sub ppb level. And when it is ultra pure water, it is at sub ppt level for ionic content concentration, and sub 5 ppb for TOC levels. So once water has been purified, as you can see from this previous slide that I've shared here, at this point we have a reservoir. So at some point, water is stored. So, but we normally recommend that the only water that can be stored is either type 2 or type 3, and it should be stored in the right solution, or a tank with the right design. But for ultra pure water, type 1 water, it should not be stored. It should be freshly prepared and used almost immediately. So mainly there is impact of water storage, and one of them is there is high risk of recontamination. So the water being an excellent solvent will be recontaminated almost immediately. And the source will be the environment in the lab, and also contamination from the container stored in. So therefore, even if it is type 2 or type 3 water stored, the right storage solution should be used. Ultra pure water is considered ideal for critical laboratory applications, and being an excellent solvent, it will pick up contaminants from the lab, air, such as carbon dioxide, the organic solvents, and so on. And therefore, it should not be really stored. It's actually, there is a regulation in ASTM that normally recommends that that ultra pure water should be stored for a very short time, and actually should be used almost immediately. So now we look at the potential impact of water on results. So mainly, the recommendation is that water should be free of any contamination that could compromise the results of any given experiment. So any analyte of interest should not be present in water. For example, for elemental analysis, the water should be actually free of any element of interest. It also should be free of any contaminants that could interfere with performance of the instrument. For example, if you're running a HPLC analysis, the water should have the lowest concentration of organics, because TOC will really affect running the HPLC. So we look at the impact of water on HPLC and LCMS. So as you can see here, like I've just mentioned, TOC levels really affect the results, and increasing TOC level results in more extraneous peak and baseline shift. So looking at this, you see experiments that were run using water that has different organic concentration. So you have 2 ppb, 5, 9, 13, and 20 ppb. And you can see the baseline is not even the same. And also there is increase in this peak concentration, meaning that as you increase, as the organic concentration increases, you have an increase in these ghost peaks that you see here. So the TOC level in water for HPLC should be as low as possible. Just to show the effects of the other contaminants, we have, obviously we've talked about the organics, which we've just seen, noisy or drifting baseline average, as you have seen, and also there is potential to have the ghost peaks, which they are known peaks. There is also pollution of the column, so there are reduced column lifetime. We mentioned this. For the ions in HPLC, they have few effects unless you're running a mass spec. Particles will damage the HPLC pumps and injectors, and also may increase the system back pressure for sure. Bacteria in water will also behave like particles, so there will be back pressure, and byproducts includes the organics now, which will obviously have the noisy or drifting baselines and unknown peaks as well. The water that is recommended for HPLC analysis or liquid chromatography analysis is low TOC, and the system should be able to monitor the TOC online. And also low in ions, so resistivity at 25 degrees should be maximum 18.2, and the system should be able to monitor the resistivity throughout the purification process. Low particles, so the system should be equipped with technologies that are able to get rid of the particles, and also should be low in bacteria. So basically the use of 0.22 micron filter is very important. When it comes to elemental analysis, here we are talking about the frame atomic absorption, inductive recoupled optical emission spectrometer, also graphite furnace, AA, and also ICP-MS. So this is how the sensitivity moves from AA all the way to ICP-MS, and therefore the increase of importance of laboratory condition in terms of sample preparation, where now water comes in, obviously the operator expertise, clean room, and dedicated instruments. So, and the increased importance of water quality, again, from AA all the way to ICP-MS. So the effect of the classes of contaminants in this is the ions will interfere with the measured elements. So there will be poor repeatability, and the blanks obviously will read high. Then we have particles that may clog the nebulizer spray chamber or form deposits on the touch of the ICP or ICP-MS. We also have bacteria that may release ions, metals or organics, and they also behave like particles, so they will clog the nebulizer chamber. We also have the organics. Again, they may form deposit on the touch or on the MS interface. Then we move to impact on microbiology analysis. This is the workflow for the microbiology lab, where we start with the media preparation and also the testing part. This is where the water quality comes in the media preparation. And obviously we have the other steps, which moves from autoclave, then there is sample collection, there is sample preparation, inoculation, incubation, and finally the reading. So water is critical from the start in the media preparation. And actually, culture media is more than 90% more than 90% of the culture media is water, and therefore water quality is very, very important. If you're using poor water quality, then there are various consequences of this. So one is the abnormal color, incorrect pH, medium inhibitory or low productivity, and also formation of precipitate. So basically, the results that you will get are not the desired result if you use the poor water quality in media preparation. There is a recommendation of the quality of water that is required. So selecting a solution for microbiology media preparation, first is water with low conductivity, so free from interfering substances. And the resistivity of this water should be above 5 mega ohm centimeter. And our systems can comfortably say that they normally produce water that has a resistivity of about 15 mega ohm at 25. Low microbiology count, so the system should be able to produce water that is free of very, let's say, low bacteria count. So mainly the recommendation is less than 10 colony forming unit per liter. And I can say that our water systems are able to produce water that has less than 1 colony forming unit per liter, thanks to the 0.22 micron filter that is used, and also the bactericidal UV lamp that are there in our water system. Also, water quality monitoring is very important. And the recommendation is to freshly prepare the water and use it almost immediately, or stored in a tank that is made of inert material. And a foot pedal would really help to make sure that we do not introduce contaminants when we are handling the dispensers. We have a water purification system that we normally recommend for microbiology media preparation water. And this is the Milli-Q IX that has 4 fluorides, 3 liters per hour, 5 liters per hour, 10 liters per hour, and 15 liters per hour that produce type 2 water. There's also more information that you can get through our partners, Cleanearth, a tech brief on selecting the optimal water quality for microbiology. So when it comes to, there is also other applications like genomics. These classes of contaminants will have various effects on these PCR-based techniques, like bacteria and byproducts will have, they will be source of nuclease and DNA, and also source of organics and ions. So organics, especially humic or fulvic acids, could bind to the DNA or interfere with the enzymes. You also have, when it comes to ions, you have iron, cadmium, zinc may interfere with enzymes. Magnesium concentration must be carefully controlled because it also affects the PCR-based techniques, and particles may deposit in line if we are using machines or automatic machines in this case. So we've just shared a few impacts of water on various techniques, and now I just want us to go through how water is purified. So because we have just seen the contaminants in the water, we've talked about 5 classes of contaminants, and obviously the water purification system should be able to remove these contaminants to levels that are not, to levels that will not affect the experiments in the lab. So how is water purified? I mentioned before we came into the market, there were only 2 purification techniques available in the market. And one of them is actually the oldest purification techniques, which is distillation. And distillation is a very simple way to distill water. So it removes a wide array of contaminants like the organics, ions, and bacteria. But it has quite a number of drawbacks. One, some of the contaminants are not fully removed. For example, you can't fully remove ions through distillation. You can't fully remove organics, bacteria, and so on. So you will still have levels of contaminants in the distilled water. The other is no control over the quality of water produced, because once you produce it at this point, and we said water is an excellent solvent. So the most you expose it after distillation, then it means that the risk of recontamination is very, very high. Again, this is a very slow process because you vaporizing the water, cooling it to get distilled water on this other end. So very, very slow. And there is high consumption of water for cooling and also energy to vaporize the water. So the electricity in this case. And maintenance, because there will be some scaling, as you can see in this photo, is also high maintenance where you use acids to dissolve this collusion here. The other purification technique was that your standard deionization. So where you use ion exchange resins, the anion exchange resin and cation exchange resin. So easy to use, and ions are efficiently removed for sure, but other contaminants, for example, bacteria, are not removed. So actually, if you have water purification system that only has deionization part only, then that water should not be used for, let's say, microbiology analysis, because there is high risk of bacteria in that water. May become contaminated with bacteria, yes, because bacteria cannot be removed by deionization, and multiple regenerations can result in water contamination by organic molecules. So these two, distillation and deionization, are the conventional way of purifying water. But then in the modern day, we do have modern water purification. So since none of the purification technology can get rid of all the contaminants, we have a combination. The water purification system has a combination of purification technologies that are able to remove the contaminants from the water. So through the two stages that we talked about, the pretreatment stage and the polishing part. But obviously at this point here, you will need a reservoir, because this is also a low process, because we are starting from raw water. So to get to type 1, type 2, or type 3 water, it's a slow process. But from here, polishing the water from type 2 to ultra pure water is a fast process. So what is inside here are these purification techniques. So you have the pretreatment pack, you have the reverse osmosis, electrodeionization, UV to control, to deactivate bacteria, and then you have the storage solution at this point. Then you have ion exchange resin, photo oxidation, UV lamp, and you also have activated carbon and ion exchange resin. And finally, before water is dispensed, there is this final polishing of water using adapted application pack or final filter at the end here. So as you can see here, each of these technique has effect on various contaminants here. These are the contaminants, and this is what we have as purification technique. This is reverse osmosis, which actually has effect on all the contaminants. Have electrodeionization just to remove ions, UV254 bacteria, UV254 in the tank again to control bacteria, ion exchange for trace ions, UV oxidation for organics, activated carbon to remove the oxidized organics to be removed by the activated carbon, and obviously the screen filter for particles and bacteria. So this combination of purification technologies help remove all these classes of contaminants. But like I said, each stage produces a certain grade of water. So from pretreatment pack to up to reverse osmosis, you have type 3 water. Then from there into this tank after EDI and UV 254, you have type 2 water. And at this point here, you have ultra pure water. So this is the purification journey that shows a combination of all technologies to produce ultra pure water. And most important to notice that we have the resistivity cells to monitor resistivity. And at the end here, there is usually the TOC monitoring of the ultra pure water before dispensing. So just to touch on a few of these technologies, reverse osmosis, about 95% of the contaminants are removed, all the classes that we mentioned. But RO membrane is very sensitive to plugging, to falling, to piercing, and also to scaling. So, and also some water is rejected at that point. So with this cartridge, after there is a force applied, you will have reject water and you will have the permeate water. So there is some water that is rejected. For electrodeionization, it's very efficient for ion removal, no chemical regeneration, because these ion exchange resins here are regenerated continuously, and it's good feed water quality. Good feed water quality is required to prevent plugging and falling. So you see here, when you use electrodeionization, the quality of water is usually constant. But when it comes to standard deionization, like we've seen before, there are at some point where the ion exchange resin gets exhausted and they need regeneration. At that point, the quality of water dips. After regeneration, it goes up or change of cartridge and so on. But with EDI, due to continuous regeneration, it's always constant. Talk about UV light 254 or 265 with the new instruments prevent bacterial growth, but not a curative solution. You have activated carbon, and this is to remove the organics, efficient removal of the organics. So it's used on the polishing side, and no other contaminant is removed by activated carbon. For photo-oxidation, this is low pressure mercury UV lamp, but in the modern day water system, we have mercury-free as well to reduce organic contamination, to bring it typically below 5 ppb. For polishing technique only, so it's used when you want to produce type 1 water. And during the presentation that was done before, there was the mention of sustainability. So there has been concern in mercury is toxic and requires specific waste management. And regulations are becoming more stringent regarding the use of sale of products containing mercury. So some of the UV lamps used in the water purification system are mercury UV lamp. And the European Union recently ratified the Minamata Convention on Mercury, one of the most ambitious policy for protection against mercury. So for us, sustainability, we are also working together with our partners to make sure that we are producing water purification systems that are sustainable. We have now new mercury-free UV lamp. So we are using in our new water purification system mercury-free UV lamp, which uses xenon excimer technology for photo-oxidation, which are environmental friendly and alternative to the traditional UV lamp. So with the same photo-oxidation properties. Same for bactericidal UV lamp. And for the ion exchange, again, we've moved to more environmental friendly ion exchange resins that has fast kinetic, the IQ nano resins, which are 33% smaller. So meaning the cartridge are much smaller. So obviously saving on the plastic and so on. So using smaller beads. And then finally, we have the screen filter, which is the final purification step. So it's usually the last purification step to remove particles and microorganisms greater than their pore size, mostly 0.22. But we also have, it's very important to note that we have other final polishers that are available based on the application. For example, we have a final filter that is tailored for water for molecular biology. It's called the BioPack. We also have LC pack that is to produce very clean water for organic analysis. We also have a VOC pack and an EDS pack. So we are able to tailor make a solution based on the application. So how do you select an optimal solution for your lab based on your application? So obviously, we have quite a number of solutions available to produce water for various applications. So we are able to produce pure water for microbiology media, for titration, ELISA, JADAL, and so on, type 2 water. And the final filter that we recommend here is the Milli-Pack and also the BioPack. On the polishing side, where you have type water for critical laboratory applications.
You know, my best.
Hello, any question from the team? Okay, so we have the ultra pure water and we have an array of final application packs, the EDS pack, BioPack, LC pack, Milli-Pack, and VOC pack that are tailored for various applications. VOC is for VOC related analysis. Milli-Pack is for bacteria-free and particle-free water. LC pack is for organic analysis. BioPack is produce protease, nuclease-free water. EDS is for endocrine disruptor related analysis. And obviously for ultra trace analysis, we have the IQ element for water for trace elemental analysis. This is ICP-MS and graphite furnace AAS. So what needs to be considered is the ease of use of the equipment, also traceability, and very important is the professional service and support and digital services. So that is why as Merck, we are partnering with Cleanearth, who are able to offer the professional service after they place a system in your lab. And just to mention, it's very important to always have the system checked in terms of regular service and maintenance. Make sure that, and also changing the consumable, because the water purification system also has consumable, changing the consumables as and when they are required, because it's only through this that you'll be assured of the quality water that you deserve. So one is the service and maintenance of the system, which include also regular changing of consumables. Make sure that you're assured of the quality of water you're getting from the system. And also this helps because if your system is not being checked regularly and you're not changing consumables regularly, it means it will get to a point where it will just stop or stall. And at that point, you will require someone just to come and do repair, which will cause a lot of downtime. So this is really very important. And also the previous presenter talked about sustainability. This is a very big topic these days about sustainability. So this is really needs to get those systems that really are environmental friendly in terms of space saving, use of mercury free, and so on and so forth. So for when it comes to ultra pure there's very need to monitor the TOC level and the ionic level, as we said, and also the particle levels and bacteria. System should be able to do the monitoring online. Water should be freshly prepared and used, and also good pretreatment. Good quality pretreatment is very important, because pretreatment of water comes before reverse osmosis, which is the major purification technology inside the water purification system. So a good quality pretreatment is key to that. Then there is also the part of flexibility, where you can tailor make the quality of water. So water quality tailored to your needs. We've talked about all these final application pack, the Milli pack for bacteria-free water, LC pack for organic analysis water, like LC liquid chromatography, EDS pack for endocrine disruptor related analysis, VOC for VOC analysis, and biopack for water for nuclease, protease, DNase-free water. So, and water purification system, for example, the IQ system can use up to 4 of these Q-pod or point of delivery. So you have that flexibility, and each of them can be fitted with the specific application pack for water qualities tailored to specific needs. The other part that we need to also check is the compliance with various norms. So the system should be able to be fully integrated data management. There is possibility of this system to archive all the information about water, and you can export this data through this USB port here. So there is a lot of traceability of water quality over time, the history of all dispensing reports, and also consumable status monitoring. So the system is able to tell you when you need to change and how to do it. The other is what I've just talked about, the need to have the system checked regularly. That is the service and maintenance, and where you require validation as well. Validations should be done, and verification and calibration services. So we have in Ghana, the Cleanearth, our partner, who are able to offer the service and maintenance, and also to replace the consumables as and when required. In conclusion, I just want to mention this, that different laboratory applications requires different water qualities, and using the appropriate water quality will help ensure accurate and reliable results. As we have just seen, a combination of several water purification technologies is required to obtain water of consistent quality. And as we speak about sustainability, environmental consideration, which may once have been considered extras, are now quickly becoming a must-have, and may lead to long-term cost savings. Finally, it's just a questions to our audience today, or our attendees today. How is your lab going with water purification? So basically, what are you using to produce water in your laboratory? Please let us know which technology you are using to produce water for your lab. And we just hope that you've been that we have shared with you a taste of what value Merck and Cleanearth can provide to your laboratory. And we invite you to continue the discussion with us or our water experts, so that we are your partner of choice when it comes to lab water solutions. Thank you very much, and I welcome any question or comment from the attendees. Thank you very much.